So welcome to the lecture on critical speed of shafts. So in this lecture we will discuss about the shaft speed at which its vibration will become, its transverse vibration will becomes of very large amplitude. So when we start the shaft and it rotates, there could be some speed at which its vibration amplitude, that is the transverse vibration amplitude, could be very large, or the shaft can vibrate violently. So this speed we call the critical speed of the shaft, and when the shaft is rotating at this speed, its amplitude will continuously grow, and it could be quite dangerous to run the shaft at or near this speed. Below or above this speed, the effect is reduced, much reduced, and therefore the amplitude of transverse vibrations are reduced. So what is this critical speed, and we should try to understand why this type of phenomenon occur in shafts. So we can see here, if we have a shaft, so we have a shaft, so here we can see these are bearings and this is shaft, and here is a disc in the middle. So here the shaft, we consider it as a light shaft, so that the, in compared to the mass of the rotor, the shaft mass is negligible. Now what is the ideal case? That this rotor or disc, this is disc, and it has its own center of mass. So center of mass of the disc is here, and this is passing through the axis of the shaft. Then there is no any problem. However, most of the time, due to the manufacturing inaccuracies, the center of mass of the disc is shifted away from its geometrical axis. So it means that if this is the geometrical axis, but the center of mass could be here. So let us say G. So G could be here, and when G is here, so it means the shaft is rotating about one axis and its mass is acting here. So due to this, there will be some unbalance of the forces in the system, and that will generate the vibration. So when we have, so let us say this is the O. Now you can see here the shaft is rotating with omega, some angular speed. This is the O, that is the point that is on the center line of the bearings. This is S. S is the geometric center of the disc, and G is the mass center or center of mass or center of gravity of the disc. So let's assume that this difference between this geometric center and the mass, mass center is E. So this E is called the eccentricity. So that is the distance between the radial distance between the mass center and geometric center of the disk. Now if the shaft is rotating, then what will happen? There will be centrifugal forces acting on the disk that will act on the G, and due to that force the shaft will move in transverse direction, and due to that there will be some restoring force that will be acting towards the axis or center line of the shaft, and that will try to keep it back to its original position. So these will be two forces acting. So here M into E is called the unbalance, and so if this E is 0, unbalance is 0, so everything is balanced and there is no problem. Now come that when we have centrifugal force, so centrifugal force we have here this distance R. So centrifugal force is m r omega square, so R plus E, because from this axis the distance is total R plus E into omega square. This is centrifugal force. Now the stiffness of this system in transverse direction at this point S is, if the stiffness is K, transverse stiffness K, and this is radius is R, so this is the restoring force is K into R. So here m R plus E omega square is the centrifugal force, and the restoring force or shaft resistance force is K into R. So if we assume this, the bearings at the end, we can assume it as simply supported, and therefore this stiffness K equal to 48 ER, because P equal to, sorry, delta equal to P L cube by 48 EI for the supports at the ends, and from here we can find K equal to P by delta, and P by delta, that is 48 EI by L cube. So K of stiffness of this shaft is 48 EI by L cube. So for equilibrium condition, these two forces will have in equal. So Kr equal to mr plus E omega square, because shaft is rotating at some speed omega at some distance r, and its geometric axis is at r plus E from the axis of the rotation or the center line of the bearings. So when we balance these two, we will find Kr. So Kr equal to m r plus E omega square, and from here we will find R, because here R K minus m omega square equal to m omega square into E. So from this we can find R equal to m omega square E upon K minus m omega square, and then we take this K by m we take this m here, so we have this k by m. So k by m is omega n square. So omega n equal to root k by m. So omega n square equal to k by m. So we can replace k by m with omega n square. So and we take omega n square out. So we will have omega upon omega n square into e upon 1 minus omega by omega n square. So we will have this expression finally that tells us that if the shaft is rotating at this particular speed omega and it has some eccentricity e between the geometric center and the center of mass of the disk or the rotor, and omega n is the natural frequency of the system, then we will have the shaft will rotate with some transverse amplitude r. So r equal to omega by omega n square e upon 1 minus omega by omega n whole square. Now here we can see that if we have omega equal to omega n, so if omega equal to omega n, we will have r tends to infinite, means we have infinitely the amplitude of vibration will be infinitely large, and this we can see from this frequency curve. We have here r by e plotted with respect to r, that is omega by omega n. So this r is different. This is the frequency ratio omega by omega n. This r is the distance from of the geometric center from the center line of the bearings. So we can see that when we omega by omega n is less than 1, so here we are omega by omega n less than 1, we have here r by e, we can see here, and at exactly 1 we are tending to infinite, and then when r omega by omega n is greater than 1, we have r by e tending towards 1. So here when we have omega by omega n less than 1 or omega is less than omega n, we will have this configuration, that is the center of mass is outside of the disk, so heavy side is here. However, when omega by omega n is greater than 1 or omega is greater than omega n, we have this light side is here. So therefore we have to avoid this condition omega equal to omega n, because here the vibration or the condition nearby omega by omega n, because whenever we are in this zone we can see that we are having large amplitude of vibration, and when now if omega is very large, we see that we are tending to r equal to e here. So we are coming to the finite amplitude of vibration. So here we found the solution of this numerical problem that was based on the derivation that we did in this lecture, and now we took the shaft where there was no presence of any damping. Now there could be the presence of damping, and the damping could be due to the air resistance, because usually the shafts rotate at very high speed. So the air resistance could be quite high, and therefore there could be the damping due to air resistance, or there could be some material damping in different type of applications. So if there is some damping in the system, then we have to understand that there will be one more force acting on this system due to the effect of damping. And we can understand from here that when there is damping, this point O, S and G will not be in one line, but there are three forces. So there will be these 3 points, so O, S, G, and we can see that the centrifugal force that acts on G, and this will be acting here, that is m omega square A, where A is the distance from point O to the G, and the spring force or restoring force is K into R here, that will work on the geometric center of the shaft. And the damping force, if we consider this air damping or resistance damping as viscous damping, so it is like C into V. So the damping force due to the damping effect is C into V, and V equal to R omega, so C into R omega into R. So this is the damping force, and this damping force will work on the geometric center of this disc, and so this is the C omega R. And so if the shaft is rotating in this direction, this will be working in opposite direction of this. So there are these three forces. Now we can see this triangle that is being formed, and this angle is alpha, and this is phi, this angle is phi. Now this resultant of Kr and C omega R will be some resultant force here, and this force and this force will provide some couple. That couple will, now we can find here. So this condition we can find from the geometry. A sin alpha equal to E sin phi, and A cos alpha equal to R plus E cos phi. Now for the forces, now if we want to balance the forces in x and y direction, so sigma x equal to 0 and sigma y equal to 0. So when we said that there will be some torque that will be acting opposite to the motion of this shaft, that is coming due to this damping effect, because this damping effect is going to generate some torque, and that is opposing the rotation of this shaft. So therefore that's why we need some power source to rotate this shaft against this motion, this torque. So for this system that should have sigma x equal to 0 and sigma y equal to 0, so we balance these forces in these two directions, and so we will find these two equations. One is minus Kr, and then the component of the centrifugal force cos alpha, and here is because this damping force is perpendicular to this restoring force, and then the sin alpha component of this centrifugal force, and we will find this, and by solving with these equations this equation can give us R by E equal to this expression. So now here we see that we are here R by E equal to, so omega by omega n, that is the frequency ratio. So let us say this capital R square upon 1 minus capital R square whole square plus 2 zeta r whole square under root. Okay. And tan phi is 2 zeta r upon 1 minus r square. So, and this damping ratio is c upon 2 root km. So, if we compare these expressions, we have already seen in the lectures when we discussed the vibration due to the force unbalance. There we found x upon m0 E by m equal to the same expression, and when we are discussing the shaft, here m0 and m are both equal and x equal to r. So, we have the same expressions. So, now if we discuss the frequency response curve, this is the same frequency response curve. Here it is r by E, okay, and we can see that the effect of damping, when we have some damping due to some air resistance, even at critical speed, that is omega equal to omega n, our amplitude of transverse vibration is not infinite, but it is finite. When damping is 0, we have infinite, but when we have the finite damping, even small damping 0.1 at the critical speed, the amplitude is finite, and when we are increasing the damping, the amplitude is going to reduce. So, therefore, if we have damping in the system, even at critical speed, we are having lower amplitude of the transverse vibration. So, now we will perform one numerical example to use this concept. So, here we have a rotor having a mass of 5 kg and that is mounted. So, rotor has mass of 5 kg and it is mounted midway on a 1 centimeter diameter shaft, and that is supported at the ends by 2 bearings. The bearing span is 40 centimeters. The bearing span is 40 centimeter. So, the length of the shaft is 40 centimeter. Because of certain manufacturing inaccuracies, the CG of the disc is 0.02 mm away from the geometric center of rotor. So, E is 0.02. If the system rotates at 3000 rpm, so it is given the speed of the shaft or the disc, then find the amplitude of steady state vibrations and the dynamic force transmitted to the bearings. Neglect damping. Take E equal to, so E is the Young's modulus, that is 1.96 into 10 power 11 Newton per meter square. So, we have to solve this problem. So, here we are given the M equal to 5 kg, the mass, and diameter equal to 1 centimeter, and that is 0.01 meter, and then we have length of the shaft, that is 40 centimeter, so that is 0.4 meter, and eccentricity E is given as 0.02 mm, or that is equal to 0.02 into 10 power minus 3 meter, and omega, that is the speed, is 3000 rpm, and we want to know R, that is the amplitude of the transverse vibration, and dynamic force, okay, and dynamic force on bearing, dynamic force on bearing when we are given E equal to 1.96 into 10 power 11 Newton per meter square. So, here we know that we have to use our that common formula R equal to omega by omega n whole square E upon 1 minus omega by omega n square. So this is the formula that we have to use. So in this we know E, we know omega, so omega we have to convert in radian per second because this is in rpm. So we can do like 2 pi n by 60, so 2 pi into 3000 by 60, so we will get 100 pi. So this is 100 pi radian per second. So we know omega. We now we have to find omega n. So omega n is the natural frequency of the system. So omega n is root k by m, and k we have to find. So k is 48 EI by L cube. Now 48 E is given 1.96 into 10 power 11, and I is pi d4 by 64. So pi into d4, d is 0.014 by 64 upon L cube. So L is 0.4 meter, so 0.4 cube. And when we solve this, we will find the stiffness K 72,000 Newton per meter. So we have found the stiffness of this system, and we are given the mass of the disk because we are neglecting the mass of the shaft, saying that it is the light shaft. So omega n equal to root k by m, and so we will find root k by m, and so k is 72,000 and m is 5, and so we will find omega n, and omega n is coming like 120 radian per second. So we are getting omega n. So we can put this in this formula. So we to find r. So r equal to, so 100 pi, that is omega, by 120 square into E. So E is 0.02 into 10 power minus 3 upon 1 minus 100 pi upon 120 whole square. So when we do this, we will find R equal to minus 0.0234 mm. So it means that we are getting negative sign, so it means that the displacement is out of phase with the centrifugal, the direction of the centrifugal force. So here this is the second case, like we have the light side case. Now we have got this R. Now we have to find the dynamic force on the bearings. So dynamic force is the restoring force, the reaction of the restoring force, because here the restoring force or the reaction force will be equal to the restoring force, and that is equal to K into R. So K is the stiffness of the system. So we have got K, that is 72,000 Newton per meter, and R we have got 0.0234 mm. So we multiply with 10 power minus 3 to convert into meter, and so the reaction force we will get into Newton. So here we will get 1.68 Newton. So this is the total reaction force, and there are two bearings, and therefore the force will be distributed equally on the two bearings. So dynamic force on each bearing that is equal to 1.68 Newton by 2, so that is 0.84 Newton. So here our shaft is in the vertical plane. Now if this is in the horizontal plane, then we have to also consider the dead weight of the rotor. So this is the final solution of this problem. So we discussed the critical speed and for undamped shaft system and damped shaft system. So now we stop here, and we will continue this lecture in the next. So thank you for your attention.